Hi, my name is Ashley Vonica, and this is my first video journal for Organic Chemistry 2. This is our Grignard addition to a ketone reaction to form the tertiary alcohol triphenylmethanol. So first thing I'm going to do is discuss the mechanism. You'll have to bear with me. I'm using my iPhone to record this, so we'll try to make this work. Alright, so the first step here, even though this is backwards, but we'll make do, is bromobenzene, and the magnesium and diethyl ether, as you can see in solution there, that is what creates our aryl Grignard reagent, the phenyl magnesium bromide. Now the very important thing to note about that organometallic reagent there is that the magnesium to carbon, the carbon to metal bond is covalent in nature, which means that the carbon side will become a carbanion. That's why it's called a masked carbanion. So as you can see, that carbanion is nucleophilic and it's also basic, which means it's very sensitive to protonation, which is very important to the yield of your product. In fact, that's probably what affected my low yield of product, was early protonation of that very sensitive carbanion. So what happens next is that the carbanion in the Grignard reagent nucleophilically attacks the carbonyl carbon of our ketone benzophenone. The carbonyl group is polar. The carbon has a partial positive charge and the oxygen has a partial negative charge. So that's what attracts that carbon of the carbonyl, attracts the nucleophilic attack of the carbanion to form a new carbon-to-carbon bond. So this is just a diagram of how that happens. The carbanion is attacking that carbonyl carbon, and then the pi electrons of that double bond move towards the oxygen to form the alkoxide ion. And in the last step, our alkoxide ion is quenched with hydrochloric acid, which protonates the alkoxide ion, creating our tertiary alcohol product, the triphenylmethanol. Okay, now I'll discuss a bit of the questions here. The purpose of this lab was to produce an organometallic reagent, in this case the aryl Grignard reagent using bromobenzene. In organometallic compounds, there is the carbon to metal bond, the importance of the differential electronegativity between the carbon and the metal is that the polarity of this bond places a partial positive charge on the metal and a partial negative charge on the carbon, making it a carbanion. The negative charge from the unshared pair of electrons on the carbon makes it both basic and nucleophilic. This nucleophilic character is crucial in facilitating synthesis reactions involving the carbonyl groups of aldehydes and ketones. The partial positive charge found on the carbonyl carbon makes it an electrophile that can be attacked by the nucleophilic carbanion to form a new carbon-to-carbon bond. Very important reactions in organic synthesis chemistry. So, why are anhydrous conditions so important for this reaction to be successful? Well, unfortunately in my case, I probably didn't have completely dry conditions. And basically what can happen is that if there's water contamination, water will protonate the carbanion, which is very sensitive to protonation, which will destroy its reactivity at that point, limiting the formation of your product. So I did get some triphenylmethanol, but it wasn't enough for any solid to precipitate out of solution. So basically this is the mechanism of what I believe happened in my reaction right here. You can see that the Grignard reagent on the right side of the screen, the carbanion is protonated by water, which creates benzene instead of our tertiary alcohol, because now that carbanion is no longer free to react with the carbonyl carbon. It's become a benzene instead. So likely that's what happened to me. Okay, let's see. So basically what happened during my experiment is upon addition of that benzophenone during week 1, I got like a frothing or foaming, which I talked to Dr. Kelly about that, and he was just as perplexed by it as I was. But he basically told me that this was probably the death of my product right then and there, that it had become protonated somehow. So basically that mechanism I just showed you was the acid-base transfer of hydrogen, a proton from water to produce benzene. So preparation of the Grignard reagent was accompanied by several key color changes in the solution. The brown iodine color disappeared after the introduction of bromobenzene ether solution, which is critical. That brown color, if it does not disappear, it means that you probably had water. Mine did appear to disappear, although I don't think the solution was very dark to begin with. So the magnesium dissolves, turning the solution opalescent. That was another key color. While only a few fragments of magnesium remain, this opaque opalescent appearance is due to the fact that the forming Grignard reagent, after you've added the benzophenone, the Grignard reagent reflects light in the heterogeneous reaction mixture. Because the magnesium did not entirely disappear, it was used in excess, and the bromobenzene in this case would be the limiting reagent. So a higher yield of Grignard reagent would be possible with the addition of more bromobenzene. It also must be taken into account that there is the formation of byproducts as well that also detracts from your final yield, the byproduct being biphenyl. And how that's formed is by a single electron transfer. And again, in my lab report, I have a picture of that mechanism right here. So the bromobenzene and the magnesium transfers only one electron to the phenyl bromide. So what happens is the formation of phenyl radicals. And then those phenyl radicals combine to form the byproduct biphenyl. So that's unavoidable. That's going to happen no matter what. So adding more reagents such as bromobenzene would help counteract any product lost by the formation of the biphenyl. The final product requires a 1,2 nucleophilic addition of the Grignard reagent to benzophenone to create the tertiary alcohol triphenylmethanol. The organometallic compound phenylmagnesium bromide acts as a masked carbanion. Alright, I'm going through my script here, and we already talked about this. The covalent nature of the carbon to magnesium bond is what makes it a masked carbanion. So let's talk about the quenching procedure with the hydrochloric acid. The magnesium alkoxide of triphenylmethanol is quenched with hydrochloric acid. The acid is used rather than a base because protonation is needed to create the tertiary alcohol. Only acids are proton donors, while bases are proton acceptors, so that's why the acid would be used and not a base. And unfortunately, the likely contamination with water in my experiment did not allow for the precipitation of solid even at the low pH. But the reason why we tested for the low pH was to make sure that the protonation had occurred, basically. That we had added enough acid for it to fully react and fully protonate our product. Another important thing to note is hydrogen bonding. So one of the questions here, let me see. What is surprising but greasy structure, benzene rings. So anyway, triphenylmethanol forms large crystals, which one can assume is similar to the organized lattice structure of the melamine cyanuric acid complex. Now, this was a reaction that we did in semester 1, which involved creating a huge hydrogen bonded crystal lattice structure with the melamine and cyanuric acid. So drawing a parallel between those two experiments, that one from last semester and this experiment, because the triphenylmethanol is a solid that forms large crystals, I can surmise that hydrogen bonding would be rather impressive to form such a structure. In fact, this is a quote that's cited in my lab report. In the crystal structure of triphenylmethanol, the molecules form hydrogen-bonded tetramers, with the oxygen atoms positioned approximately at the corners of a tetrahedron. So that would account for any impressive hydrogen bonding. Now, a brief discussion of the infrared spectral analysis. So basically, the major difference between our starting products, particularly the ketone, the benzophenone, and our tertiary alcohol, is that the benzophenone had a large carbonyl peak at around 1649, which would be missing in the tertiary alcohol because that's replaced by a large broad peak indicative of oxygen-hydrogen stretching. So show that to you. This is our benzophenone IR spectral data right here, and you can see I've marked where the carbonyl peak is at 1649, that large peak right there, which is not present in our final product. Instead, what you see is this. Right here, you see a very large, broad peak that corresponds with the hydroxyl group of the tertiary alcohol. And there's also a couple of this right here. Those 4 peaks are stretching vibrations of the benzene rings. Alright, I believe I've answered all of the questions. We talked about masked carbanions, we talked about the IR spectral data, about quenching with acid, about the color changes, anhydrous conditions. So it looks like I'm all set. Alright, thanks, I'm signing out.